oct3ene. Okay? Notice how for this one, I did not put the A after oct. I did not make it octa. I just put oct3ene, and you could also write 3-octene if you prefer to do that. Both are correct. Okay, so that's dealing with our parent. Now we can talk about our substituents. Right? So what do we have coming off of the ring? Or coming off of the chain? We have a methyl. We have a CH3, another methyl. We have a bromine, and that's it. And I think out loud for you guys, like if you want to answer, like answer. By all means, that's why I do that, is so that you guys can think what I'm thinking and we're, on the same wavelength. So our first ones were methyls. We have 2 of them. So I'm going to put dimethyl. Right? And then where are these coming off? The first one is coming off of 3. Okay. And the next one is coming off of 5. So I put it like that, okay? Now let's deal with what other substituents we have. Bromo, right? We have that bromine, and it's coming off of which carbon? 5. Very good. All right. So it seems like we've dealt with all our substituents. Is there anything else? Stereochemistry. So we dealt with all our substituents. Now, like he said, we're going to deal with stereochemistry. So we have 2 things we have to show the stereochemistry for. If there's a double bond with different groups attached, and if there is a chiral center that also has 4 different groups attached. So where is our chiral center located? On which carbon? 5. Yes. So that's what we're going to, I think we'll deal with that one first, and then we'll go back and deal with the double bond, okay? So this is going to be our con, prelog, Ingold, naming. R or S, okay? The configuration about this carbon, where are the atoms located in space, okay? So we're going to pick their priority based upon same thing, atomic mass or atomic number. So let's look at the 4 groups we have. Which one will be our highest priority?
The bromine.
The bromine, very good. So I'll put that as 1. And then I'll move forward. So what would be my second group? We have 2 carbons, right? So 1 carbon, the one that's number 4, right? That one is also attached to another carbon, double bond, so 2, CC. And then in addition to that, lowest priority would be hydrogen. Make sure that you put these in order. Don't put it as hydrogen, then carbon, right? Make sure you still stay true to the highest priority. And then for the next one, what do we have? We have a carbon, like the number 6. We have a carbon attached to 2 hydrogens. So we're going to pick the one that has the double bond as our number 2. So I'll put a 2 right here. That's talking about, that's our second priority group. And then our third one would of course be the chain that's coming off in comparison to the methyl that is a carbon attached to 3 hydrogens. So we will pick 3 like that, and we will pick 4. Okay, so we've written down the priorities, and now we just have to make sure of one thing. And that is that our lowest priority group, so the number 4, whatever that number 4 is, it should be going away from you in space. In other words, it should be on a dash, not on a wedge. Here, what do we have it on? We have it on a wedge, so that's a problem. So we want to change whatever we calculate, whatever we solve for, we are going to change it to the other. Okay, and there's different ways you can do this. Some people will look at it and they'll say, from before they number anything, 1, 2, 3, 4, before they've done anything, they'll look at it and they'll ask themselves, is my lowest priority group, which is commonly hydrogen, in this case it's methyl, it's commonly hydrogen, is it going away from me? And if the answer is no, then they will swap 2 of the groups, solve for R and S, and then change their answer. That's if you have a hydrogen in the plane of the paper, that is the best method to do it, okay? That is a way to ensure that you will never get it wrong if the hydrogen is in the plane of the paper, okay? In this case, it's the CH3 is not, so we'll just go as this. So we draw an arrow from 1 to 2 to 3 as such. Okay? And if you go clockwise, if you make this motion, think about you're drawing an R on your paper. I draw it like this. Oops. When you're drawing an R on your paper, you go like that, right? You see that? You go clockwise, right? That can help you to remember. Or you're going to the right as well, which it starts with an R. So that's how you would remember that this would be R. So you solved and you got it to be R. If you went the other way, it would be S, left. So R, and then our lowest priority group is not on a dash, so we are going to swap it, cross it out, just to remember why we changed it, and then take it to S. Does that make sense? Why that's S? Okay, awesome. So we found that at that number 5 carbon is S, so I'll just box it for now until we write the entire name out. And then we will go to our double bond and deal with E and Z, okay? So let me erase all this junk in the way. So at our double bond, cut it down the middle as such. Take the left side for what it is. Which group is heavier, the bottom one or the one on top?
The bottom.
The bottom one. Very good. So it's because you have a carbon attached to another carbon versus the top one is a carbon attached to 3 hydrogens. So you will pick the bottom one as your heavier. Does that make sense? Now let's move forward to the right side, right? So we have, I'm going to draw a little hydrogen coming off just so we have something to compare. So of course this big group that's going down, the bottom group, is going to be a heavier group. It's a carbon with a bromine and CH3, and also another carbon. So for that reason, I'm going to write H on the bottom. So I'm going to ask you guys, are these on the same side? Yes. So we're going to name it as Z. Okay? All right. So we got S and we got Z. So now we want to write our entire parent name. There's not a lot of space. Oh yeah, there's space here. Okay, so starting from the beginning, we want to put our stereochemistry always first, like we did with cis and trans. And we're going to start with whichever one is at an earlier carbon. So our double bond is at the 3rd carbon, right? So we will put our parentheses, and we will start at that 3rd carbon. And then we will indicate that we got Z. Okay? And then we put the comma. And we'll also put R and S within the parentheses. And so we need to also indicate where that's coming off of. Is it the 5 carbon? 1, 2, 3, 4, 5. Yeah, so it's the 5 carbon, 5S. Okay. Then we put our dash. Now we have to draw our entire parent, and we have options of what to put, in what order. Which one are we going to put first? Bromo or methyl? Bromo, good job. Alphabetical order, and then after that we'll put a dash and then fill in the rest. Methyl, and then of course there should not be a space after the L in methyl, but I ran out of room, so I'm just going to put the oct 3 as such. Okay. Do you guys have any questions about that?
What was the other way of writing it? Or with the 3-octane?
Yes, you would put 3-octene.
Oh, just in one word? Okay.
Yes.
So would we prioritize the double bonds over the number of substituents?
Would you prioritize the double bonds over substituents? Yes. So your double bond is such a higher priority that it is going to be a part of your parent. So yes, you would, of course. You would look at the substituents if and only if you have double bonds located left and right? The same. So if you had a 1,3,6 and 1,3,6, then look at your substituents and see the numbering and so on. Yeah.
Really?
All right.
Oh, yeah.
So let's look at number 3. Do you guys have any other questions? Yes. No. So the reason why, so let's look at what we have.
What was your question?
Oh, her question was you don't do cis or trans for this one. So the reason why is cis and trans is if you have the same group, like two methyl groups, or if you have, let me do this. Like this, for example. Okay, you see how between these guys they're the same group, they're both CH3s, so it would be perfectly fine to just say that these are cis. In comparison, then if you swap one CH3, put it at the bottom, then you would say that these are trans. But what we're doing, so E and Z is like more specific than cis and trans. So what we have here is that they're different groups. You see, between the two different carbons involved in the double bond, they're different groups. So that's why you should use E or Z. If they were methyls, both methyls, then yes, you can use cis and trans. It's easier. What's up?
How do you choose where to break it?
Where to break it? For deciding E or Z?
Yeah, for like to count like the heavier.
Yes, of course. So it's kind of messy here because it has so much written, but you would break it straight down to the double bonds. Just like that, straight down the double bond and take the left side for what it is and then take the right side. Sorry? Oh, well, in this one there's only one double bond in this. Oh, the first question.
And you didn't pick the
Oh, yes, good question. So, for the first question, I picked this double bond right here. Right? And the reason why is because you only have to indicate E or Z if it's internal double bond, not for external double bonds. Because you have two hydrogens, so they're the same group. So how would you be able to determine which one is higher priority? Does that answer your question? Okay. Okay, so let's continue on to the third one. And in the instructions, it told us, don't knock down my camera.
I will not.
So it says, following the required conventions, draw a proper Fischer projection for the compound N3. Okay. And the reason for this is because you have,
Just in case. I don't want anybody calling me. You're good.
like,
Yeah, I
do
just
not
put it down here.
disturb? Oh, if your mom calls you or something? Don't hang up on your mother. I did it once. Gosh. Okay, so we're doing, for this right here, you see how there's two stereo centers, right? Two chiral centers indicated by 3s and 4s. So that's the reason why we're going to write this in the Fischer projections, because it will show you R and S. Okay, it's an easy way to write it. So let's start. When you're given the name and you have to draw what the molecule looks like, I find it easiest to look at the parent first, write that down on the paper, and then add your substituents in, right? So what are we given? We're given heptane. So I want to get my parent chain, I want for it to have 7 carbons. So that's what I'm going to do. And I know that I have 2 chiral centers, so I'll draw those first as such. Right? This is the Fischer projection. So at these, what's the word, cross-section, is that the word? Or intersection, you have the stereochemistry is going to be shown, right? So those are your chiral centers. At every single one of those, you have a chiral center, and so that should be, let's write in the numbers, that should be your 3 carbon, and then the one below it should be your number 4 carbon. So we're assigning those 3 and 4. And then we need to write the rest of the parent. So those are including 2 carbons, right? Our entire parent is how many carbons? 7. So we want to make sure that we include that fact. So if we have 3 and 4 here, then that means what is attached up here will be our number 2 carbon. We're going up to bottom, okay? And then our number 1 carbon, I wrote it right there. So let's number it 1, 2, and we got 3 and 4. And now we still are missing, to get to our heptane, we are still missing 3, right? So let's write our 3. So we're going to have a CH2, a CH2, CH3, and now let's number 5, 6, 7. Okay, so right now we have heptane right now, assuming that these are hydrogens attached. It's just showing it as a Fischer projection, okay? Now we can start looking at our substituents and where they're coming off. So let's start with our 4-methyl, right? Coming off of our 4th carbon. So that happens to be one of our stereocenters. So what I'm going to do, I'm going to take a guess. Like this. And put my CH3 at that 4th carbon, okay? We're good so far? No questions? Okay. And then we'll look at what else we have. So we have dibromo. So that means that at the number 1 carbon, we're going to have a bromine. So let me go and erase the hydrogens that I put, right? And we'll make it a CH2 now, and we'll add a bromine to that, okay? And now we also have a bromine at our number 3 carbon, right? So I'm going to take a guess. We're going to go and check our work to make sure the stereochemistry is correct for these. That's the best way to do it. But we're going to put our bromine at our number 3 carbon. So we have everything written on the paper. Now all we have to worry about is our stereochemistry, okay? About the 3 and the 4 carbon. So let's use our naming system and solve for that. So we're looking at the number 3 carbon first. And so what would be our highest priority group? Bromine. Boom. So we'll put that as number 1. And then what would be number 2?
Top.
So we have a top over here. So let's see. So let's test it out. So we have, if we went the top way, we would have a carbon, right? And that's attached to a carbon. And it's also attached to hydrogen, right? And then if we went 4, let me indicate that this was carbon number 2. Okay. And then let's write down carbon number 4 as well. Okay. So that is going to be carbon. And what is our carbon attached to? It's attached to a carbon, right? Another carbon, and a hydrogen. Yeah. Okay. So let's keep going. So if that's the case, where's Chance?
Sorry.
Oh my God, it's so hard to see you. For sure, I just want to check with one thing with you. So the number 4, we would go with that because it's attached to the carbon, right?
Yeah. So
Okay.
it's CCH versus CHH.
Yeah. Okay. I just wanted to confirm that because there's a bromine coming down. There's a bromine later on. So be very careful with something like that, okay? So we were thinking that, oh, the top one would be high priority, but you have to go down the line, okay? So our number 4 has the carbon and the carbon. So we're going to put what's going down as our 2, okay? And then let's erase this guy. And then this right here is going to be our number 3. And then, of course, our hydrogen is number 4, right? And now, let's draw our arrow going from 1 to 2 to 3 and ignore wherever 4 is located. You just go straight. Okay? So if we were to go like this way, which letter should it be? R or S? S. Good. And then we ask ourselves, so with Fischer projections, you need to imagine like a bow tie. So everything that is horizontal is coming at you in space like a bow tie would come at you. Okay? Everything that is vertical is on a dash. Okay? So that means that our hydrogen, our lowest priority group, is coming towards us in space. So we'll cross this out and we go with R. Right? So let's compare to our original molecule. Okay? Our original molecule, it gave us that we want it to be 3S. So do you see how there's a discrepancy if we were to write it this way that we did guess and check? So there's a discrepancy, so all we're going to do is the single swap rule, where you're going to take this bromine, erase it. Take this hydrogen, erase it. And you're going to swap them. So you're going to put the bromine on the other side, and the hydrogen on the left side. And then whenever you switch two carbons, their orientation about a chiral center, it changes it from R to S or S to R. Single swap, that will change it. So that means that what we have at the top, the number 3 carbon, is correctly indicating S. Does that make sense? Any questions about that? No? Okay, we have tutors going around. What's up?
Why'd you number it this way? Not 1 and 2 on the top.
Like, why did I pick the...
Numbering that way, yeah.
Why did I pick the bottom group as priority?
Yeah, not the top.
Yes, so that's what we were kind of talking about. That if you have, at your 4th carbon, right, you have a carbon. So you ask yourself, what do I have coming off of that carbon? You have a carbon and a carbon and a hydrogen. You see that? This carbon here, number 4. See how it's a carbon, the CH3 has a carbon, and then that propyl has a carbon, and then there's a hydrogen also. So that's CCH, versus if you compare to the top one, that CH2 is connected to a carbon in addition to 2 hydrogens.
Wouldn't it be carbon, carbon, bromine for the top one?
So let's look at this carbon specifically, right?
Yeah.
Because we're talking about the number 3 carbon, right? So if we look at that carbon is directly attached to a carbon, right? It's not directly attached to the bromine. There's still a carbon in between.
Okay.
You see what I mean? So you have this. And so you go straight down the line, and these are same tie, and then you look at this, the carbon is higher priority than the hydrogen, so that's why we went with that one.
Okay,
Make
thank
sense?
you.
No problem.
And why did you switch the hydrogen and bromine?
Why did we switch the hydrogen and bromine? Good questions. So we calculated it out to be R, right? Looking at what the question is giving us, it wants for us to write 3S. We don't want to write 3R. So we just did a guess and check. We found the stereochemistry. We found that it was incorrect, so we swapped 2 atoms, and that would give us the correct stereochemistry. So if we went now and found what it was, we would get the S that we're looking for. Good question. So let's go forward and look at our number 4 carbon and do the priority for that one as well. So our highest priority group, would it be the group coming up or the group that's going down? Like, would it be the number 3 carbon or would it be the number 5 carbon? 3. Good job. Very good. So you have a carbon attached to a bromine, right? Attached to another carbon, attached to a hydrogen, right? Versus if you went down, so if you took your number 5 carbon, right? Because we're talking about the number 4, but we're looking at the number 5 in terms of priority. And so you have a carbon, and that carbon is attached to a carbon, and a hydrogen, and a hydrogen. We go down the line, bromine is definitely going to be higher priority than would be the carbon. So we are going to go with the group that is going upwards, like when you're looking at the plane of the paper upwards, that will be our number 1. Does that make sense? Okay, so I'm going to just put number 1 and circle it to indicate that one is heavier. And then the group that's going down, of course, would be number 2 because it's a carbon attached to another carbon versus the CH3 is a C attached to hydrogen, hydrogen, and hydrogen. So that's why we picked that as number 2. And then now we're going to compare our CH3 to a hydrogen, and which one is higher priority? CH3. So you put that as number 3. And then our hydrogen, of course, will be lowest priority. Now what we want to do is calculate or solve for R or S. So if we go from 1 to 2 to 3, so ignore 4, right? Go straight like that, right? We're going like this. So we're going clockwise. So that would give R, right? But pay attention to your lowest priority group and ask yourself, is it coming at us or is it going away from us in space? It's on a wedge, right? So because it's on a wedge, we got to flip it, okay? So it will go from R to S. So that means that stereocenter, so number 4, is an S naming. So our question wants us to write 4S, right? So that means we guessed correctly, good job, and we can just leave it as it is. We don't have to swap anything, and we can move forward. So we would write that as our answer. And of course, in your box, I would probably just keep it without the wedges and the dash. I was just doing that to show you what it would look like in space, but I would just write it as such. And then put your bromine going to the right. Keep that stereocenter the same, and then CH2, CH2, CH2. I'll put this in your box. Are we good? Do you have any questions about that? No questions. We're good? All right. Take your pictures. Okay. And now we'll move forward to facts, my favorite section. Let's check if this one has, okay, so it doesn't have the table for the bond association energies, but,
Oh yeah, this is one.
Oh, yeah, this one, yeah.
I can,
Yeah. Everything.
I'm just going to tell you guys what those energies are, and I will show it to you how it would be written on the table, okay?
Yeah, I was trying to put up here.
Okay, so let's start with facts, you guys. So let's read what it says. It says, using the bond dissociation energies, BDE, from the table at the end of the exam, calculate the overall delta H standard for the reaction in the box provided, and you must show your work below, in the box below, to receive credit. Alright, so let's just start off with like our definitions and all of that. So for bond dissociation energies, what are those? So that's going to be the amount of energy that you have to input in order to break a bond apart. Okay, the name is, let the name help you to tell you what it is. How much energy you input in order for these atoms to dissociate, right? So that would be whenever you're breaking bonds, you input energy, okay? So that should be a positive number. Whenever you're breaking apart bonds, you're releasing the potential energy that was in that bond, okay? And then it says, calculate the delta H standard. So in order to do that, I wish there was some more space here, but I'll try to fit it on the side. So there's going to be a formula that you have to use, and you can use the BDE values in order to calculate the delta H. So we're going to start with the bonds that you're breaking. So you're going to put the sum of the bond dissociation energies for the bonds. Okay, positive value, right? Now we want to subtract from that the bond dissociation energies, and this is also going to be the sum, right, for the bonds that are formed. So I'll put formed. Okay, and that is going to be equal to our delta H standard. Alright, so we need to look at what we're given, this reaction, and we need to decide which bonds have been broken and which ones have been formed. Use those values from the table, input it into this equation, and we'll get the answer, okay? So let's look at what we're given. So we have this molecule here, and we have HBr, and it seems as though the OH is going to be replaced with a Br, and then you're also going to form water, right? So that means that we are forming a bond between this carbon right here that I'm trying to highlight and bromine, okay? We're forming a bond between those. So under bonds formed, I'll say that we're forming a carbon to bromine bond, right? And then in the table, you'll see it if you were to look at it. It will let you know if it's like a secondary carbon or tertiary carbon or primary carbon, because it would be different values for each of those respectively. So the carbon that we have here is a secondary carbon. So I'll just say like secondary carbon attached to a bromine. That bond has been formed, and so I put it there. Okay. And then let's look at let's start with what was broken. I probably should have started with what was broken because that's how it goes sequentially. So we have broken a carbon to oxygen, so carbon to OH, hydroxy group. We have broken that bond, right? So I'll put secondary carbon to OH group under the BDE bond broken, okay? And then what else was broken is that it seems as though this bromine here, right, it came from the HBr. So that means the bond between the H and the bromine was broken. Okay, so I'll put that HBr, that bond was broken as well, right? Because the bromine went to the carbon and that hydrogen went to the oxygen to form H2O. So what else was formed? OH bond between this and this. And what else is also present on that oxygen is an H, right? So you're forming this bond right here. I'll put a little line between it. And you're forming this bond between the carbon and the bromine. And then the bonds that are broken are this and this. Does everyone agree? Does that make sense? Okay, so now all we have to do, once we found that part, go to our table, and I don't have it attached to this one right here, but I will just look it up. I mean, on the table, you'll see, like, it'll have a carbon with, like, 2 CH2s attached to it or something like that to indicate that it's secondary, and then it will show you that there's a bromine attached. And so let's look at the secondary carbon attached to OH, for example, and here I don't have them moved.
Yeah, we got it.
So I have it right here. Yeah, thank you though. Yeah. So we're first going to look for that secondary carbon. So I have it right here, and it says that it's 91 kilocal over mole. So I'll put 91 kilocal over mole. I mean, all the units are the same, so I'll just ignore them for now. And then what was our other bond broken? It was the HBr, right? So I would go on here, and you see like HX. And you go to the HBr section, and you find 88. So I'm going to add these guys to each other. Okay, because we're breaking bonds, so you're inputting energy, and then we'll subtract to say that what comes after was bonds that were formed, and there's going to be 2 of those, so there will be a section about bonds to secondary carbons. And then in that section, you'll see if you formed a secondary carbon to a bromine, you have 68. So I'll put 68 like that, and then we add these together, and we'll add it to if you had an H to OH bond, and here it's given to be 119. Okay, so I put 119, and then you just do the math in your head, and you will get your answer to be -8. Okay. And here you should include your units, that it's kilocal over mole. So that's how you do the part A, okay? I'll leave it there as we go to part B. It says, are the products or reactants favored at equilibrium? So of course for these reactions in organic, you'll have it going to the right and also to the left. They're going both ways to form both your reactants and both your products, right? So the delta H standard value, depending on its sign, it will let you know which side of that equilibrium is going to be favored. right? So this is similar to the delta Gibbs free energy. The change in that, if it's negative, it means that in that direction, it is spontaneous, right? So here we have a -8 delta H enthalpy, so that means that this forward direction is going to be favored because you're releasing heat. You're releasing energy in the form of heat. So for that reason, I would put that products, because it's a negative number. If it was a positive number, it means the reverse reaction would be favored. Do you guys have any questions about that? Okay. Let's continue to number 2. You want to mention stuff?
No, I'm just.
Oh,
So we're halfway down with time.
okay. I'm gonna have to go a little bit faster. So if you guys are not understanding something that I'm saying, then please ask one of the tutors, okay? And they'll break it down for you. So for number 2, it says place the compounds below in order of increasing bond dissociation energy. So same idea for the indicated bond. And then it has lowest BDE would be 1, and the highest would be 3. So what we're going to do is with BDE, you have homolytic cleavage right down the middle. Homo meaning that you'll have one electron go to one, and then one electron go to the other atom. Okay, so I'll draw it on each of these that are indicated, right? That's where it's getting cleaved, and you have one electron going here, and you have one electron going here, one electron going here, one going here, one going here, and one going onto the carbon. So the arrows are kind of hard to see. So since we showed that part, I'm going to just show you what gets formed. So what's important is that you're going to form a free radical at all of these. All right. So at each of these, you're forming a free radical that has one unpaired electron, and we need to compare these guys in according to their stability, okay? So if we have like an energy diagram, right? So let's say that this is our starting molecule, right? This is where it is in terms of its energy level, okay? And you have to input some energy, break that bond, and then it's forming something that is less stable. So it will be forming something that is higher in energy, right? So we have these 3 options, so I'll just put 3 different lines, okay, to indicate each of them, okay? So we need to compare these in terms of their stability, and then we will go from there in terms of BDE. So if we're looking at the first one, you have to ask yourself the degree of that carbon, what is it? And so this would be a primary free radical, okay? The one in the middle is a 1,2 secondary free radical. The one at the end is attached to 1, 2, 3, so it's tertiary. So your trend in terms of stability for free radicals follows the carbocation trend of stability. So it's going to be more stable on a tertiary carbon than it is on a secondary carbon than it is on a primary carbon, okay? So which one of these guys is the most stable? This guy. All right, this is the most stable. So if this is the most stable, that means that you input the least amount of energy. It means that it's this right here. You see that change in energy? It's smaller, so you input less energy in order to break it apart because you're going towards something that is more stable. So the bond dissociation energy would be the lowest. Okay, and then we'll continue. So our secondary would be the next most stable. So our secondary would be in this box right here, in this line, right? So that would require a little bit more energy in order to break it apart. So for that reason, we will put it as second. And then, of course, the primary is the least stable free radical. So for that reason, it would be our number 3. You have to input more energy in order to create something that is so unstable. Okay? And that's for that question. And if you have questions, please ask the other tutors, just so we can try to get to everything. Yeah. In the box, draw the transition state of the rate determining step for the reaction of 2-chloro, 2-methylpropane with CH3OH. Okay, so there's also like a lot of definitions going on here. I would start off probably by writing down the molecule itself. So let's start. So we have propane. So that means you're going to have 3 carbons. And then you're also going to have, so if we numbered it like 1, 2, 3 as such, then at our second carbon, we're going to have a chlorine. So I'll put the chlorine like that. And that's, what else do we have? And also at our second carbon, we have a methyl group like that, okay? And that's all our substituents that have been indicated. So from there, I'm just going to fill in this right there, okay? And I want to point out something for this this question in particular, because when I took this exam back in the day, not back in the day, like literally 2017, but the key for this on Dr. Bean's key, the answer was accidentally written incorrectly. So if you're looking at the key that has been posted, or you have the key, just be wary of that. It has the wrong answer. Okay, so this is something that they graded it wrong on my exam, and I went back and got the points back, but because the key was wrong. So yeah, so let's continue what we have, and then it's going to be a reaction with CH3OH, right? So we have methanol, and we have an alkyl halide, right? And we need the rate determining step for this reaction. So that means the step that has the highest activation energy, okay? The transition state is the most unstable. So when we're looking at this, I look at my nucleophile. Okay? This is SN1, SN2, E1, E2. That's stuff you have to have it really, really down pat, okay? It's so important. So for this nucleophile here, it's neutral, right? So it's neutral, so that means it's not going to be a strong nucleophile, okay? It will be a weak nucleophile. Methanol is a weak nucleophile. And then you look at your alkyl halide, which is the other molecule, and what degree carbon you have a tertiary carbon, right? So the fact that I have a tertiary carbon, right, and I also have a weak nucleophile, that needs to point you in the direction of one particular reaction between the SN1, the SN2, the E1, and the E2. Actually, it could point you in for 2 of those reactions, but the way that they happen, the first step is the same, which is the rate determining step. So let's take SN1 and E1, okay? The first step, which is the rate determining step for these, is going to be the leaving group, which is this chlorine, is going to leave. It just leaves on its own. Chlorine leaves, you form a positive charge on that carbon that it left, okay? So it's starting to get, that carbon is starting to get a little bit more positive, right? This chlorine is starting to get a little bit more negative, and this is what we need to put in our box. So we'll keep everything that did not break or did not change, we will keep it consistent, right? The same. Now, the carbon to the chlorine, that bond started to break, right? So I'm going to put a dotted line like such. Let me see. Yeah, it doesn't really look that dotted. Here, I'll make it like that, right? To the chlorine for the bond that is breaking. Now we are going from a neutral carbon in our alkyl halide, we're going from a neutral carbon to one that will have a full positive charge and be a carbocation. So for that reason, what's in between a +1 and 0 is partial positive. Okay, so I put partial positive on that carbon, and then on the chlorine, you're going from a neutral chlorine to something that will be a chloride. So it has a full negative charge. What's between full negative charge and 0 will be a partial negative charge. So I put the partial negative on the chlorine because that's where the chloride is forming. Okay, and if you have any questions about the mechanism for this, please ask one of the tutors because I have to get through it all.
What's the answer? The 6?
That's the answer, that's it. So you just need to know that the rate determining step is the first step in SN1 and E1, and it's the leaving group leaving to put that positive charge. It's not the nucleophile coming and attacking the full positive charge. Okay, so let's look at the next one. And we say place the following carbanions in order of increasing stability. 1 is equal to the least stable, and 3 is equal to the most stable. So I believe that this was supposed to be on exam 1, I believe. But let's look at it. So we have these carbanions, and our trend for the carbanions are going to be primary will be more stable than secondary, which will be much more stable than tertiary in terms of degree for where the carbon with a negative charge is located. So the first one, we have a secondary, right? For the next one, we have a primary. And for the last one, we also have primary. All right? So right away, which one is going to be the least stable?
The first one?
Yeah, the one that's secondary. Because you're comparing a secondary to two primaries, and primaries are more stable carbanions, okay? Those electron donating groups are increasing the negative charge of that carbon that has a negative charge. You don't want that. So then now there has to be some point of difference between the middle option and the far right option, right? They're both primaries, so there has to be something to distinguish them. And exactly, I heard it, the R word, so resonance. You have this carbon is adjacent directly to the double bond. So what that means is this guy can come down, right? And these pi electrons can come onto that carbon. Now looking at the other one, you cannot have resonance with those, or I should draw it coming from there. You cannot have resonance with this lone pair because the double bond is too far away. So for that reason, if you have primary with resonance, the one with the resonance will be stable, more stable than the one without it. So we'll put it as 1, 2, 3 down the line. All right, let's move forward to number 5. And it says, place the following alkenes in order of increasing stability. 1 equals least stable, 3 equals most stable. So this is something that Dr. Bean will introduce tomorrow a little bit more about the stability of the alkenes, but it's pretty straightforward. All it is that the more substituents that you have that are attached directly to that double bond, the more stable the alkene is due to the hyperconjugation. So you go to each one, and it looks like it's already kind of been filled out. You go to each of the double bonds, and you circle your groups that are coming off of it, not hydrogen, obviously. So you have 1, 2, 3, so that would be tri. Right? Then you go to the next one, and you count coming off of that double bond. You have 1, 2, 3, 4, so that would be tetra. And then you go to the last double bond, and you have 2 groups coming off. You see, I'm highlighting here. Maybe it makes it a little easier to see. And that's going to be di. Okay? So the one with the most substituents will be the most stable. So for that reason, I will put the one that's in the middle, the tetra-substituted alkene, I will put that as number 3. And the one at the beginning, I will put that as number 2. And the last one will be number 1. Okay? And if you have more questions about why, I can explain it to you for sure. Maybe once we get through all of this, okay? Please ask questions to the tutors though. Anything. Okay. So now we're getting into the stereochemistry part of the exam. And we have to label these pairs, right? So these are relationships between 2 molecules. Right? One molecule on its own, you would not call it an enantiomer. It can only be an enantiomer to another molecule. They're in a relationship. So you have, your options are identical, structural, enantiomer, diastereomer, okay? So let's look at the first one, and as we go, I'll try to help with defining these guys. So I would suggest to start it off, try to confirm that these are structural isomers or not structural isomers, okay? That is the first thing I think that you should look at, because why waste your time looking if it's an enantiomer or diastereomer if we already established that they're structural isomers, okay? So we'll look at the first one, and that just means, structural isomers means that the connectivity is different. So that means the condensed molecular formula, so how many carbons, how many bromines, how many hydrogens, all the atoms, is the exact same. The difference is how these guys are connected to each other. The structure is what's different, okay? So we'll look at this molecule that we have here. We have a carbon, and that carbon is attached to an ethyl group at the top. This carbon is also attached to an ethyl group. That carbon is attached to a hydrogen, so is this one. This one is attached to a bromine, this one attached to the bromine, and this is attached to a CH3. So do you guys see why these would not be structural isomers? They are connected the exact same. So there's something else about them that is making them different from one another, or maybe they're identical. We don't know, now we'll find that out. So let's cross out structural isomers for this one. Our options are identical, enantiomer, or diastereomer. So let me give you just a brief overview. So the enantiomers are going to be it's a long word, non-superimposable on a mirror image. And these guys will be mirror images of one another, okay? That goes for enantiomer, so I'll put an arrow so you don't, if you're looking at it later, don't get confused. So diastereomers are also going to be non-superimposable, so they're similar in this way. I'll just put non-super. And then the way that they differ is that they're also going to be non-mirror images. Okay? So both of these enantiomers and diastereomers are non-superimposable. You cannot put them upon their partner so that they line up the same way. It's like my hands. Now I cannot lay my left hand on top of my right hand. No matter which way I place it, I cannot lay it right on top of it unless if I cheated and I went like that. So that's what it means by non-superimposable, and mirror image is self-explanatory. So let's look at this one here. We have one chiral center, okay? So that just means 4 different groups attached to a carbon. And so diastereomers can only be an option if you have more than one chiral center. Okay, so that narrows it out. That helps us a lot, right? That can only be an option if you have 2 or more. Let the di, the di, right? That's the prefix for 2. Let it help you out in reminding you that you have to have 2 chiral centers or more in order to have a non-superimposable, non-mirror image. Okay, and the more you do, I think it will make more sense. So let's cross that out, because now we only have 1 chiral center. So we got it down to 50-50, that's good. So it's going to be either identical or an enantiomer, and how we're going to do this the easiest and most systematic way, in my opinion, is to just calculate RNS for each of them. You take each one for what it is and you calculate it. So let's look at the one on the left. So what would my highest priority group be? The bromine, right? So I'll put the bromine as 1, and then after that would be my ethyl group. After that would be my methyl, and hydrogen will be 4. Okay? If you have any questions about why I picked 1 and 2 and 3 and 4, please ask the tutors. Okay, so then we're going to go from 1 to 2 to 3, like that, right? Counterclockwise. So if we're going counterclockwise, that's going to be S, okay? And then is our lowest priority group going on a dash away from us in space? This is a Fischer projection. So remember, the Fischer wearing his bow tie. It's coming at you in space. So we're going to swap it from S to R. So our molecule on the left has a configuration as R. Now let's go and do our molecule on the right. So we would label it the same exact way atoms, like bromine would be number 1 here, and then ethyl would be number 2, methyl would be number 3, hydrogen would be number 4, and we're going to go from 1 to 2 to 3 to 4. If we get the same letter, so if we get R again, then that means that these guys are identical. If we get a swap, if it changed, that means that these guys are enantiomers, so they're non-superimposable, and they're mirror images, okay? So let's go like that. So that should tell us that this is R, but is our lowest priority group on a dash. So our lowest priority is the hydrogen, right? And it's on a wedge, so for that reason, I'm going to swap it and make it R. So I got the left one, I got R, and the right one, I got S. You had a full conversion to the other one, inversion to the other. So for that reason, these are enantiomers. If we got R, then these would be identical. Okay?
So it's supposed to be dashes for it to be identical?
Like if your hydrogen was on a dash,
Yeah?
then yeah. If your hydrogen was like where the bromine is and it was on a dash, then you would get R, and then they would be the same. And so it would be identical. Do you guys have any questions about that? No? Okay. I think now we regained some time, so we're good now. Let's continue with B and see what we have. So we're going to go down the line. Like I said, let's start with the structural isomers, okay? When we're comparing these two guys, we'll look at what each one is connected to. So this top carbon here, there is a 1 carbon that is attached to a aldehyde. This is called an aldehyde when you have CHO. So it looks like this. That's what it would look like. And then it's also connected to a hydrogen and a bromine, okay? Now on our other molecule, I'm going to look at the carbon that also has that aldehyde attached, which would not be the top one, because that has CH2OH. This bottom one here has the aldehyde, CHO attached, right? So then I'll compare what are the other groups attached to that carbon. Here you have CHO that matches with my other one. What else we have? We have a hydrogen that matches with the other one that I highlighted. And then what's left is a CH3. That doesn't match with the bromine. So it means that the connectivity from atom to atom is different. So if the connectivity is different, then what should be our answer right away? Structural. Yes, so I can only imagine spending like all the time to calculate for 1, 2, 3, 4, 5, 6 chiral centers to find R and S when you could have just done that and got your answer. You see what I mean? Just to save you some time and prevent myself from making silly mistakes. So we'll go with structural, okay? And if it helps you to rotate that entire Fischer projection on the paper by 180 degrees, you can rotate it on the plane of the paper, right? In order to line up the aldehydes, it helps you to visualize it. For sure, that is a good idea to do it. So now we're going to do the last one. And with these, let's first check, is it structural isomer? So the first carbon is connected to bromine, hydrogen, CH2OH. This one is also connected to the same type of atoms. And then the middle one is connected to hydrogen, CH3, and then also the same group coming from above, and the same group coming from below. And then the third one, same idea. H, CH3, CH2Br. So these guys are not structural isomers. So after I figured out that part, it means that I need to, it becomes a little more difficult, like I have to solve for the rest of it. So I don't want to erase all my groups. Okay, so now we're going to go line by line at each of the chiral centers. And this is up to your personal preference, which way you like to do it best. I think that there's a way that may be faster than if you want to go to each chiral center, each one of these guys, and you want to find R and S for every single one, and you want to compare them to one another, right? By all means do it. You may not have to do that. You could get to the answer some other way. But what I want you guys to know before we look at this, our options, remember, are going to be enantiomers, identical, or diastereomer. So let's say our answer was identical, okay? Just to explain a point. So if our answer was identical, then that means that at all of these chiral centers, all three of them, you would have to have like R, R, and R, for example. We don't know, but for example. And then the other molecule would also have to be R, R, and R. The configuration at every single chiral center has to be the exact same for them to be identical, okay? It could be S, S, and S goes to S, S, and S. Or it could be R and R and S goes to R and R and S. Okay, that would give you identical. Now he's staying the same, but all the other ones have swapped. So for that reason, just save yourself, guys. Save yourself. Nice, save. You can do that every time. I mean, let's if we were to go down the line, right? If we were to go down the line, the first ones you can tell just looking at them side by side, it's been switched. Two groups have been switched. And what did I tell you about single swap rule? When you swap two groups at a chiral center, it changes it from R to S or S to R. The middle one looks the exact same, so it did not switch. The one at the bottom, it switched. Right? So that means that now if on the left molecule it was R, that means on the right molecule it got changed to S. So for that reason, whoa, there's a lot. If you guys have questions, like ask me, and you can ask me. Just raise your hands, yeah, because I'm like, what happened? Everyone's dying. What's up? Yeah, let's look at it. So, here's a good question. So, I drew the dotted line, right? That's my mirror. Oh, this guy? Oh, that's really hard to be able to just say, just because the left one is in this Fischer projection, and the other one looks more like a tripod. So the other one has this CH2, CH3, and then it has like three groups coming off like the Mercedes. Like if you had a wheel, a car wheel, you lift three things, and you just rotate it like this. But the other one is Fischer projection, so you have two groups coming at you, and the other two groups going away from you. So really, it's really hard to be able to determine just by looking at it. It's much easier to just do RNS, okay? Guys, what are y'all talking about? I want to know. Are you? Is it a gossip? Okay. Any other questions? I'm sure you guys have questions. What? Should work every time. Yeah, should work every time. You look at each one, see if two groups got switched. If they didn't, then that means it's the same. What else? Okay, so diastereomers. Let's move forward. Label the compounds as chiral or achiral. And so what chiral means is that within the molecule, so you can have a molecule, and you can have a molecule with chiral centers, right? But that doesn't necessarily mean that the entire molecule itself is chiral. So when you say chiral, chiral means that there is no internal plane of symmetry. Okay? Now, if you were to cut it in half, like you cut your pizza in half, one side has pepperonis and the other side is supreme, that is going to be chiral. Okay? No internal plane of symmetry. Achiral is the exact opposite. You have an internal plane of symmetry. So that just means that it can be superimposed upon its mirror image. Something that is achiral cannot, something that is chiral cannot be superimposed upon its mirror image. Okay, so when they ask you chiral or achiral, we're talking about the entire molecule, cells does it have an internal plane of symmetry? So let's look at the first one. And with these, I honestly recommend just doing as many of them as you can, as many molecules as you see, it will help you. Because it's hard for me to kind of like tell you guys, because it's up to your own perception. So if you were to look at the one on the left, and you were to take it from, imagine my hands is like, that's my hands. Giggle, or sorry, race. Sorry. So if you were to take my hands, and you, like imagine my hand has a knife in it, and I went like this, from the top, down the bottom. Then you look at the left side, and you look at the right side. The right side, so I'm gonna kind of trace it like that. So one side will have half of a hydrogen and half of a chlorine, and the other side will have half of a hydrogen and half of the chlorine, because you're cutting it just like this, right? And then for the rest of the molecule, you see how these methyl groups, same, double bond, half of the double bond is in one side, half of the double bond is on the other side. And this bridge right here, half of it is on one side, half of it is on the other. So you have an internal plane of symmetry, so what should be our answer? Good job. All right, so we're going to look at this one right here. And so these can be a little tricky at first. So this is just called an alkene. Right? So it just means that you have a carbon in the middle, and then there's going to be two double bonds on either side. And it takes a very interesting look in space. So this is kind of hard to show you. I looked up on Google like a molecular model. So if anyone here has a molecular model kit, I don't have one, but if you have one and you want to make it out and see it, that's the best way. Just Google chance. Can I Google something? Sure. Thanks. Thanks, Dan. Ooh, ACS. Shameless plug. What? Shameless plug. Let's put. Are you hungry, guy? Who near me? What embarrassing thing. Stop it, guys. So we have Alene. Let's put. There's literally one picture, and it will help you guys. I don't know how else I'm going to explain it. Molecular model. Okay, that one is kind of good, but there's one here, please. And it's such a small picture too. Okay, look at this, guys. So this is what it would look like in space, and those flappies, those are representing, or the paddles, those are representing the pi orbitals. Okay, so one of the carbons. So let's take the left one, right? Yeah, let's take the left one, and it has these two groups coming off in the same plane as that carbon, as the gray ball. Now, if you look at the other side, it's also in the same plane, but in a different plane from the other carbon on the other side. So it's going in space, it's like this, right? But the other side was like this. Okay, so if you guys can see this, you need to imagine this every time when you, in my opinion, this is the easiest way to do it. You need to imagine this when they give you what they have on the paper. So on the paper, the left carbon is going to be the one that gives you a wedge and a dash. Okay, one is coming at you and one is going away from you. And then the other side, the one that's in the same plane, those are going to be the ones that are written as lines on the plane of the paper. Okay, so now let's transition here. You guys see it? It's convenient that it's the same format. So the Cl and the CH3, one is coming at you, one is going away. And then on the other side, you have the Cl and the CH3 going one up, one down. So if you try to cut this guy from up to down, you would have one side would have the Cl. So the problem, you guys, what are you gossiping about? Like, I want to know, please. Please. So this guy no internal plane of symmetry, so what would be our answer? Carbon. Let me give you an example. If I had the chlorine replaced with CH3, what would be my answer? There you go. Two different groups coming off from that one with the wedges and the dashes. Exactly. The other side does not matter to have different groups. Okay, let's look at the next one. So you just want to divide this guy in any way that you can to get it the same to be on the left and right or the top and bottom. So if I cut it down the middle, it's different from left to right. But if I cut it, so you try down the middle, then you try horizontal. Those are your two options. If you cut it horizontally, do I have an internal plane of symmetry? Yes, you do. Because don't let this OH like deceive you. So the oxygen is attached directly to that carbon. So it should really look like that. Maybe they're trying to trick you. I don't know. Maybe it's a typo. I don't know. But it should be like that. So everything mirrors the other side. So we have an internal plane of symmetry. So for that reason, what should be our answer? So no, yeah, thank you. I was referring to what was above, but thanks for asking because yeah, that is a BR. Yeah, that is a BR. It just I just wanted to let you guys know that it's an OH that is mirroring an OH. So don't just let the way that it's written deceive you. Okay. So, exactly. So the bottom half will have half a bromine, and the top half will have half of the bromine as well. So it's mirroring itself exactly. Does that make sense? Okay. Now let's do number 8. So in the box provided, and this is the fun stuff, guys. Not fun. When I say fun, not that fun. But in the box provided, place the letter of the reaction with a faster rate, and if the rate is the same, write same in the box. Okay, so this is where you really gotta know your SN1, your SN2. Let me put it. I like to put my SN1 and SN2 both on the left side, and my E1 and my E2 both on the right side, so that we can divide them down the middle. So I'm gonna give a brief synopsis, but of course I know you guys are gonna have questions. I know you will. So please just ask. So SN1 and SN2, the name is telling you they're going to involve nucleophiles. Okay, the N is standing for nucleophilic substitution. You have a substitution of some nucleophile. The elimination reactions are both going to involve bases. Okay, so if you want to help you remember that you have a big E at the end of base, E1 and E2 are going to involve bases. SN1 and SN2 are going to involve nucleophiles, okay? The smaller numbers, so you need to relate these guys to each other, and I think that's the best way to learn it. Otherwise, it's just a lot of stuff. So 1 and 1, so SN1 and E1 are going to involve weak nucleophile and base. Weak is your keyword, okay? So the lower the number, the weaker the species. And then for your 2, so your SN2 and E2, bigger number, stronger. Okay, so you're gonna have your 2 strong guys there. So your SN2 will have a strong nucleophile for the N, and then your E2 will have a strong base. Okay? So that's one part of it. Now we need to talk about the substrate, which is called an alkyl halide. So as the name tells you, you just have some alkyl group, right, attached to a halogen, right? So depending on the degree of that substrate, it will take a different reaction, okay? So the odd guy out for all of these 4, the odd guy out is going to be SN2. I'm going to circle SN2. SN2 is the only one, whoa, it got quiet. SN2 is the only one that will take primary over secondary over tertiary. Because the nucleophile matters. So nucleophile matters when it's coming and attacking that electrophilic site, this partially positive carbon due to the dipole moment between the bromine and the carbon. This right here, there is a partial positive on that carbon. So when your nucleophile is coming and attacking, it happens in one step. You need to make sure that there is not a lot of stuff in the way. So stereochemistry is important. So that is why you want primary over secondary, way over tertiary. Okay? The other guys, will relate them all to each other. They are all the opposite trend. So these three, we'll put them as a team. They're all going to be tertiary, gets favored over secondary, gets favored over primary. Okay? And then, of course, there's going to be some other factors involved, like our solvents, but we'll address those as we go through the questions, okay? I just wanted to give you the main, really important stuff. So let's look at A. We're talking about rate. So reactivity, rate, same idea. We're talking about kinetics, okay? We're not talking about the stability of our product. We're talking how likely is this to happen, okay? At what rate? So let's look at our first one. So we have this alkyl halide, and we have this alkyl halide. They're exactly the same. They're both primary. So there's no difference there. Let's ignore it and move forward. A bromine is what's called leaving group. It's stable on its own, so it's more likely to leave. And then what's on our arrow, we need to compare what's different. So if you were unsure and you're like, oh, I don't know if this is SN1 or E1 or SN2 or E2, I don't know which one it is, look at your substrate. In these questions, you can look at your product, sorry, not your substrate. Look at your product and see what is happening. What we had was the leaving group bromine get substituted with an iodine. So that means we will rule out E1 and E2, and we will debate between SN1 and SN2. Okay? Are you guys with me so far? Then we're going to compare what is different. So what is different is what is on our arrow. All right? These are the same. You have NaI and NaI. That Na is just a spectator ion with a positive charge. So that means you have iodide. So iodine with a minus charge is iodide. And then you need to ask yourself, well, right away, these were primary alkyl halides. So as I was telling you before, we can rule out all the others and go SN2. So if you're asking yourself, like with these, it's nice because you can use different factors to help you. Like if you're unsure about something else, use another thing and try to let it stimulate something, some thought process. So we decided that these are SN2 reactions because it's primary alkyl halide, and then you have an iodide, which is a strong nucleophile. And remember, SN2 and E2 want things that are strong, okay? So we decided based upon that. If you want a way to remember these strong nucleophiles, there's a very silly mnemonic. I didn't come up with it, but it goes, bro, I really suck corn nuts. Shit. But hey, you guys, if it works, use it. Don't doubt it, just use it. And then this SH is going to be the bad word part. So then you have, bro, I really suck corn nut shit. So that's your minus charge. So notice your similarities. Wow, this is the first time people actually really laugh at this. I'm happy. So these guys are strong, guys. Write them down. It's a strong nucleophile. So we're going to be using these guys commonly in your SN2 mechanism. All right. Notice something what's similar about all of these. Negative charge. Boom. Whenever something has a full negative charge on it, it's going to be strong because it's unstable. It's bearing a full negative charge. If something has partial negative charge, it will be weak, whether it be base or nucleophile. So we see our I. Oh, sure, yeah. I'll sometimes write it down. So we have our iodide there, and so now what's different is our solvent. So our solvent is the liquid part that is the majority of our solution. So that's going to be comparing our H2O and acetone. And so this is one other factor that you need to know when you're comparing, when you're talking about SN2 and SN1 as well. The solvent can help right? And an acetone is an example of an aprotic solvent. SN2 prefers aprotic solvents, okay? I'm getting close to 9 o'clock, so I'm just gonna say aprotic is good for SN2, so we're gonna put our B in the box. The rate will occur faster when you have an aprotic solvent. Please ask questions if you have, because we're getting closer to 9. And then we have the other one, we also have primary. That's convenient. We also have primary alkyl halide. And what do we have? So both of them are getting substituted. So that's leading me towards the left end of our table. And then we're going to look at our nucleophiles. We're going to compare them to one another. One of them is bearing a full negative charge on an oxygen. The other one is also bearing it on an oxygen. But the difference between them, very key, is that the top one will have resonance. So if something has resonance, it means in terms of stability, it is more stable. Okay? And for SN2 and E2, you don't want things that are coming to attack, you don't want them to be stable. You want them to be reactive. That's what makes them strong, right? So this, the bottom one, would be stronger of a nucleophile. It's not included in our list in the mnemonic, but it is still stronger than the one on the top because it's not resonance stabilized. So we will go as B. They are inverse. What do you mean they're inverse? Oh, I'll leave it for you for a couple of seconds. More reactive, 100%. Less stable people are more aggressive. You can remember that. Alright, so we need to get through reactions. I'll leave it there so you can write it down if you want to. We have this NBS and we have light with it. I'm going to give you guys a hint. If you see light on this arrow, it's going to be one of two things. It's either going to be with NBS or it's going to be with Br2. So you're doing free radical halogenation. That means you're going to take a hydrogen somewhere on this molecule and replace it with a bromine. NBS is specific for the allelic position. What is the allelic position? It is the one that is directly attached to the double bond. Not directly, it's like 1 over. It's not this. I need to have an example to explain that. But basically, it's going to be the carbon that's 1 over from your double bond, okay? It's not the carbon of your double bond, that's the vanillic position. This is allelic, so it's 1 over. And you have to make sure that you have a hydrogen there. So we have 2 hydrogens here. And here, do we have any hydrogens? 1, 2, 3, 4. So it's tetra. So no hydrogens are available. You have to have a hydrogen there for the bromine to replace it. So that means one of our products, we'll just go ahead and draw one of them, is that hydrogen is going to be replaced now with a bromine. You guys see that? You're replacing this hydrogen with a bromine. Now, there's 2 boxes, so that means that there was something else going on here. So let's go and draw. You guys need to remember like propagation and initiation. This is so ugly. So, remember this? We get a free radical. You had homolytic cleavage there. 1 electron came onto that carbon. So what can you do with this? You can have resonance. You can move this down 1 electron, so half-headed arrow, and this one can also move down, and then the other one in that bond can move on to the other carbon. So now we have displaced, just like when we do carbocations and stuff, put the double bond here. We move that free radical to another carbon. Does that make sense? I put it in the box. I should have put it down here, and I'll put our product in the box. Sorry. That's not the what? Which one? Yeah, it does. Yeah, don't make that mistake. Don't be like me. So the methyl group definitely stays. We don't want to forget that. That's like a curious mistake. Yeah, alkene, our bromine radical went like this and formed a bond right there. So these would be our two products. Okay? So moving on to the next one, let's see what we have. So we have alkyl halides. So we have a lot of different halogens on here. We have one that's connected to the benzene and then the chlorine and the iodine. So these are all good leaving groups. They're stable on their own. But let's look at what we have on our arrow. So we have this sulfide thing. So remember from our mnemonic, so the really sub part, what does it look like? It looks like R attached to S with a minus charge. That's exactly what we have here. So R group is just representing an alkyl chain of any kind, any carbon chain. And so that means I'm going to write, when you do these guys, try to write down like what you know, figure out what you don't know. So here we have a strong nucleophile. And our solvent is a protein. If you look up the structure for, what is that, dimethyl sulfoxide, if you look up its structure, you'll see that there's no acidic protons on it. That's what makes it a protein, okay? So that's our solvent, and that is perfect. We have an SN2, like by the book definition, okay? And then we'll look at our alkyl halide, and we want to use what degree alkyl halide. We want it to be primary over secondary, way over tertiary. So we'll look at the ones we have with our leading groups attached. This one right here is going to have 1, 2, so we got a secondary right here. And the one with the iodine is 1, 2, 3, so that's tertiary, right? So is anything going to happen at this tertiary? No. So I'm going to just cross it out so I don't get confused. And I'll put at this guy right here, I need to pay attention. We're talking strong nucleophile, so SN2. It's going to come and attack at one time, right? Concerted mechanism. Here we have a leaving group that is attached to what hybridization of that carbon? sp2. You have 3 electron groups coming off of it, so it's sp2. This is a little mnemonic. You can have no SN2 on sp2. Okay? That unhybridized p orbital is like blocking the way for that nucleophile to come in. So no SN2 on sp2, so nothing is going to happen there. We're only going to focus on the chlorine now, okay? So let's draw like the rest of our structure that ignores, and you can put a circle for the benzene if you want. So we wrote the rest of our structure that ignores our chiral center here. So we need to be paying very close attention to the stereochemistry. It has been indicated for us. So with SN2, how does the stereochemistry go? 100%, I heard it. Yes, so you're gonna get what's called 100% inversion. So if you take my umbrella, for example, and there's a strong wind and it gets pushed into the other way, that's inverted. It got inverted. So it's the same idea here around this chiral center. So the chlorine will now go on a dash, and the hydrogen will now go on a wedge. Everything got inverted, single swap. So if it was R in the left, now it became S in our product, okay? Converted, right? So 100% conversion for that guy. Sorry? Oh yeah, sorry. Pretty good. So the chlorine would be replaced, but what I mean is the nucleophile would replace the chlorine, right? And it would be on a dash, whereas the chlorine was on a wedge. Does that make sense? For if you have like a nucleophile trying to go and attack, then I would say, ooh, that's a toughie. I wouldn't want to tell you an answer and not be correct. So, what do you guys think? Andres, Chance. I'm like the only one I can never find is Chance. So let's say they had an SN1 reaction, can you attack, like if you try to do SN1 on this guy here. So it's secondary, right? So that doesn't rule it out, but it is sp2. So the thing is, what is the first step in SN1? Your leaving group is gonna leave. So when your leaving group leaves, what are you gonna form? You're gonna form a carbocation, but it's gonna be right on that double bond. Like that, right? So a positive charge on that carbon right there would be very unstable. You need to remember, this is the rate determining step. So this is unlikely to happen. When it's tertiary, it's more stable than otherwise. But having that sp2 carbon now become 1, 2 sp, right? Because this is sp now, right? Because you have 2 electron groups. So sp with a positive charge on it. No good, no good. Very unstable. So it's not likely to happen. So my answer would be no. Good question, though. So let's move forward to this one here. So what we have, ooh, this is good. So we have an F oxide, right? So we have a full minus charge on this oxygen. So that means that this is a strong, something strong, right? Is it going to act as a nucleophile or a base? That is our question here. It's not one of our strong nucleophiles in our mnemonic, right? But let's look first at our alkyl halide. So let's look at the degree of substitution of the leader, right? This guy right here has 1, 2, 3 carbon groups attached, so it's tertiary, right? So right away, that needs to rule out SN2, okay? So you're gonna go with E2, because it's a strong base. Whenever you have something strong, it's gonna end in 2. Alrighty? So elimination reactions, we haven't done one yet, but elimination reactions are going to eliminate a hydrogen, hence the name, and the leaving group. And that's going to form a double bond. Okay? You're removing 2 sigma bonds to form a pi bond. So your products for E1 and E2 will both have double bonds. What is important in terms of the stereochemistry for E2, you want to make sure that the leaving group and the proton that will get abstracted by our base are going anti-coplanar to one another. So are they going anti-coplanar in this conformation? They're going in the same direction. Anti means opposite directions. Syn means same direction, like cinnamon, right? So these right here are both on display. So they're in the syn conformation, not the anti. So what we have to do is we need to rotate one of these guys like a tripod in order to get the hydrogen on the other side, or the proton. You can pick that. Whichever carbon you want to rotate. So let's just take the first one for example, okay? We're gonna pick this chiral center. We're not changing the configuration. We're just rotating conformation.
The
So
bond though, not the atom. Yeah.
that goes there.
They're made of p orbitals.
This goes
So
here.
if your SN2
Hydrogen, we want it to be where that benzene is. We want it to be anti. So I'm making this
to make
spin,
that's your p.
and I'll rewrite exactly what I have after this spin has been
S,
completed.
2 p's, right?
So we got this.
Because your third p is busy.
Let's see. So we moved the benzene. We moved it up
How many pi bonds?
there. We moved the CH3
No pi bonds, exactly. So
there.
what are they? How are
And we moved the hydrogen to the left. Does everyone see that? Follow the arrows. The reason why we spend it is because we want it to be in the conformation where the hydrogen
SP3.
and the leaving group are anti-coplanar. Opposite directions, but still in the same plane. You see how if I put one arm like this and one arm like this, they're still in the same plane. They're parallel. They're parallel, doesn't matter, but they're just pointing in opposite directions. So that's what you want to do. That's why you're doing that. Does that make sense? Okay, perfect. So then what we want to do is, as a base would does, this happens all in one step. We've got this that comes, abstracts our proton, pushes these electrons in the bond right there. What does that do? Can't have five bonds, right? This is going to come off. Leaving group leaves. Then we form a double bond. So I'm here, and I know that there's gonna be, these two groups coming from each carbon. Now, it matters where you put these groups. It's like, dang, everything matters. So you need to remember your Fischer projections. So everything that is vertical, and remember this is a benzene, it's kind of, I wrote it funky, but everything that's on a dash is going to be going away from you in space. So everything on a dash here, they should be coming off from the same side of your alkene. So if it's my benzene rings, I'll put my benzene rings both coming up like this. Okay? Same side because they're both on a dash. The groups that are on wedge, so our hydrogen left, bromine left, we got these CH3s left. So we're gonna put CH3 and CH3 on the same side because they were on wedge before. I'm just gonna put this like for reference, so when you're looking back later, these were on the dash, and these were, that's the reason why I put them that way, okay? I think that's like -3. No, that's like, yeah, it's -3 for putting them on the wrong carbon, okay? So just pay attention to that, okay? Any questions? We're at 9 o'clock. Dang. So let's look at this one here. We have OTOS, and so OTOS is a very good leaving group because it stabilizes that negative charge. And so what we have over here on the right is a bulky base. You have those 3 methyl groups. And then we have our leaving group on our alkyl halide. So whenever you see bulky base, right away you should be thinking E2. Okay? So that means one of these hydrogens is going to be abstracted in order to push the electrons onto the bond and push away our leaving group, okay? And so, which one is it going to do? When you have a bulky base, a big base, okay? When it comes to abstract, it's going to have an option, left hydrogen or right hydrogen. It's going to go and abstract the one that is closer to the periphery. So let's draw this like that. So this is opposite of what you would normally get. Right? Your major product is going to be different than if you had a small little base like this guy. Pick the one that will give you the lesser substituted product. And that will be the hydrogen that is more exposed. Yeah. Does that make sense? It will be the hydrogen that has less alkyl groups coming from it. Like you see the one on the left, it has that 1, 2, 3 alkyl groups, the one on the right doesn't. So when you form your double bond, that right one will be less substituted. And we'll show it now here, so hopefully that will help you out. So you have a double bond that formed there. Right. So let me check everything looks good. Yeah, so we formed our double bond in the lesser substituted side. So our double bond is di-substituted, 2 groups coming off of it, versus if we abstracted the other hydrogen, which will give us our minor product. And just feel free to go like if you have to. I'm sorry that the time is kind of tough. But I'll be here till the time we have to be here. So this one goes here. We still have CH3 coming off like that. That's what I mean. So the one on the right is tetra-substituted, it's more substituted. The one on the left is not. It's less substituted, okay? Okay, so let's move forward. So here we have H2O. So that's going to be weak, no charge. So it could be acting as a weak nucleophile or weak base. Sure. I'll put it there so you take a picture as we're talking. So the major one, it has dot, it's dot. So it has this group coming off that I'm trying to highlight, and it has this group coming out, and the others has it's external alkene, so it has 2 hydrogens, versus the other one is tetra-substituted, yeah. Oh, I'll leave it there in case you want to take pictures. So yeah, so H2O, it kind of picks its role depending on the day, depending on the conditions that you or it can act as a weak base. So we're first gonna go with the weak nucleophile, so that's gonna be, if you have SN1, for example, right? Weak base would go E1, okay? So let's look at our alkene, let's see what we have. So we have one leaving group, so that's convenient, we don't have to worry about that one. And so this one right here that has the leaving group, let's check what is its degree. So it's going to be tertiary, right? So that means that SN1, the leaving group is going to leave, right? And we're going to form a carbocation at that carbon. So I'll just, for time's sake, I'll cross this out and put a positive. Right. We formed a tertiary carbocation, which is perfect for both SN1 and E1. The first step is the same for both of these guys. So for SN1, you're going to get two products. Okay? When you have an sp2 hybridized carbon, it can attack from both sides of the plane, one from below and one from above. So for that reason, you get what's called a racemic mixture, where you have one product was inverted and one product was retained. So you have inverted product and retention. So let's put one of them. So this is our CH3, nothing happened over there, so we'll keep it exactly the same. And then we'll look at our carbonyl center that we're talking about. So the bromine, right, let's do our retention. So it was on a dash. So that means our nucleophile, which is water, it's giving us that OH that's going to get added. That's going to get substituted. So we have an OH that's still on a dash, and we'll have the ethyl group still on a wedge. Okay? And then, so this is our retention, same stereochemistry. Versus the other one, we're going to draw it exactly the same. The only difference, whatever was on a wedge, we will now switch to dash. And whatever was on a dash, we will switch to wedge. So that means that our CH2, CH3 will now be on a dash. Before it was on a wedge. And on our wedge, we are going to put our nucleophile that came and attacked. So that is our OH group, okay? That is our inverted product. Okay, so that's our SN1 at the top, and then there's two other boxes. So whenever you have SN1, most likely you're going to have E1 as well. Because the first step is the exact same, and the conditions are the exact same. So for the E1, our product needs to have a double bond in it. So we're going to look at the carbon that is adjacent to the one with the leaving group. So there's a couple here actually, so we're going to have plenty of options. So I'll cross this out and put H and H, okay? And we're going to have our weak base, so now he changes roles. He's going to act as a weak base. And a base goes and abstracts a proton, right? So which one is it going to check? Here they're not asking about major or minor, so, but we do have these three different options. So really, as long as you put one of these threes, they should give you full credit. Let's check it. Yeah, so this is kind of deceiving because they give you two boxes, but if you put one of three answers, you get the right answer, because you cannot differentiate between two. I'll show you them now. So if we were to take our H2O, it acts as a base goes and abstracts a proton, right? So let's go here, abstract this proton, and this is not the correct mechanism. A carbocation was formed. I was just showing you like for the purpose of what happens, but let's say a carbocation is formed here, okay? Leaving group leaves, carbocation is formed here, you have hydrogen here, so then what happens is H2O gonna come here, abstract our proton, push the electrons onto that positive charge to get rid of it. You see how it's different from E2? You form the carbocation first, and then the base or the nucleophile will do its job, okay? It's not at the same time. So we're gonna form our double bond there, so we'll write that product, the one that we get from this. It's gonna form right there in between, bromine left. Now we have an sp2 hybridized carbon. So these are all in the plane of the paper. So now you don't have to worry anymore about the stereochemistry. And then hydrogen had one, form a double bond, and then all we have to worry about is what was on other sides of the molecule, which is the CH3. So that's one of our products, and this guy right here would be tri-substituted. Okay, and then we can pick between, for the next part, we can pick between this hydrogen or this hydrogen, right? So if we were hypothetically to pick hydrogen A, then we would form the double bond there. I tried to mark it there. We would form it there, right? But if we were to abstract the hydrogen from B, B and this guy coming down are the same thing, like this one. It would come down here and form our double bond there. So if we were to do it that way, we would get an alkene that is also 1, 2, 3 tri-substituted. Okay, and when we write it out, I think it will be easier to see. And if we abstracted A and we formed that, it would also be 1, 2, 3 tri-substituted, okay? So all of these are tri-substituted. That's why you cannot pick which one would be major product, more stable, because they're all tri-substituted. So I can show both the options of what you could get. So let's say that proton A was abstracted, electrons come down, form a bond there, you would form it right here, right? And then you would still have a CH2, so the ethyl group, CH2, CH3 coming off from that side, okay? Now if we were to add or in the box, and if you're ever confused, like during the test, I remember during the exam, I raised my hand and made sure, and I told them, oh, both of them are tri, so is it okay if we put, and they were like, yeah, it's okay. You know what I mean? So just ask if you're ever unclear about that one of the teachers. So then, the other one, if we were to abstract B, what would happen is that would come down, so our double bond would not form within the ring, it would form just outside the ring. Do I see that? It's involving that first carbon that was first the CH2, and then now, what do we got? So we have this, bromine had left, and then that one became the double bond, and then that carbon lost one hydrogen, so now it has a CH3 coming off like that. So you could write any of these in your box and get it correct. Okay? E1, SN1. I'm going to zoom a little bit. You can still see it. It's probably hard to see still, but as you guys take pictures or whatever, I can read the next question. So it's asking for a mechanism, and it will give you the products, right? And you have to use arrows to show the electron flow. And you have to remember to show only one step at a time. And you want to show all the intermediates and formal charges and no transition states. So for these, what I would suggest, right, so for this exam, we're doing these 4 guys. These 4 reactions. Okay, so it's going to be one of these. And somewhere in there, you're going to have carbocations. You'll notice trends. The more you do, you'll notice. You're going to form a carbocation. And then you're going to rearrange that carbocation. So let's compare our reactant to both our products. So we have 2, we have A and B, right? So if we're going to compare it to A, just like from a broad spectrum, we see nothing happens to that methyl group on the left. On the right side, we see that an OH has somehow been introduced, bromine has left, that should be triggering something. And then also, a CH3 has moved to another carbon, and then everything else was the same, okay? For the one on the right, we see that a ring went from 5 to 6 carbons, so there's some expansion somehow. And then we also have a substitution. This H2O must have come and attacked and given us that OH right here and right here, okay? So right away, we need to forget about E1 and E2. We need to focus on substitutions. So this could be SN1 or SN2. Now we'll look at what our nucleophile is. Our nucleophile is a weak nucleophile, H2O, and there's E. So that should be a hint to you that this is going to be SN1. Okay? That it's going to be SN1. Was that your question? Exactly. that's what I'll do. I'll show this just leaving. So I'm writing everything the same. All that's changing is my leaving group left, and so that means that that carbon is now going to gain a positive charge on it. Okay, we formed what is called a carbocation. Okay, so when you're doing these questions, you need to form that carbocation first, and then take what you want to do from there, okay? It's going to involve a carbocation. That's how you can get these products that look completely different. Well, not completely different, but look pretty different from what you're given, okay? So we formed a positive charge there. And so in the next step in SN1, we typically will have some weak nucleophile come and substitute itself, add itself onto that positive charge. But if we look at our products, we don't see the OH getting attached at that carbon. Let's look at our products. You see how it looks kind of analogous, but the difference is that the OH is not at that carbon, it's at this carbon. You see the difference? It's at this carbon. That's what you have to notice. So once you notice that, it means that something has to move. Something has to rearrange, and we need to displace our positive charge somewhere else so that we can have our weak nucleophile water come and attach itself at that location. Okay? So how can we do that? How can we move a positive charge? You have to have a rearrangement of either an alkyl group or a hydrogen. Okay? So you can have a hydride shift where a hydrogen with its two lone pairs move, or you can have an alkyl shift where, for example, in this case, we have a CH3, right? You can have that CH3 move with its lone pairs over to where the positive charge is, and it will move our positive charge to where it left, basically. So we'll redraw everything the same, like that. Okay. All we did was we broke the bond where the CH3 is bonded to the ring, we moved it over, and we attached it right here. Does everyone see that? So if we do that, that means where's our positive charge going to go? It's going to go where the methyl left, right? That carbon is losing electrons. So you put it here. Now you should start to see how we get to our product. If we have the H2O, weak nucleophile, can go and attack that positive charge that is located there. So at that carbon, you formed a bond between oxygen and carbon, right? So look at the rest of your H2O, right? You still have a hydrogen and a hydrogen, two hydrogens, right? Still attached there, and you still have a lone pair. One of the lone pairs went into creating the bond, and the other one is remaining there. So we're going to put it as a positive charge. 1, 2, 3, 4, 5. So we do 6 minus 5, and that gives us positive charge, formal charge for the oxygen. So you have to indicate the formal charge, okay? So we got that. Now, notice how in our product, right, it has been deprotonated, right? Like there is no longer two hydrogens, there's only one, and it's neutral. We want our product to be neutral, so we're going to do a deprotonation, okay? We're going to remove a hydrogen, and you can use some base in the solution. So if you wanted to use water, you could use water, or we could also use the bromine. So this is a weak base, but so is water. Did I forget about the other in here? I just forget about the CH3s. But yeah, so you're gonna use your bromide to come and abstract this guy, push the electrons onto the oxygen. When that happens, you get to your product K. You guys see that? So you can use any weak base that you have in there. You could use H2O, you could use bromide. Use that to go deprotonate that acidic proton and then form the hydroxy group right there in A. Okay? Now, for our next one, I'm gonna change our color to make it a little bit more clear. So E1, or not E1, sorry. We also are gonna have SN1 because we see an OH group that has been substituted, right, for bromine, but now the ring has changed size. So that means that when we had formed our carbocation in our first step, there was a rearrangement using the ring. So the ring itself expanded. So I'll show it. So the first part is going to be the same. So it's forming this right here. That's going to be the same. You formed your carbocation, bromine left, right. So I'm not going to rewrite that. But what I can do is I'll just put like an equal sign or write like same thing, just to indicate that I know that it's the same thing and that they know that I know. And just write down the same thing that I had at the top, okay? And then we still have this. Okay. This is where, honestly, it gets tricky to try to visualize how this ring goes from 5 to 6. Okay, so let's look at our product here. Right, we have our carbocation, and what we have is this. We know that that carbon there must at some point get a positive charge. Okay, because that's how the hydroxy group came, or the water came and attacked it. So that has to eventually gain a positive charge. Okay, and that is also going to have a methyl group attached to it, right? And then you also have a CH2, CH3, and a CH3. So you can kind of look at what's coming off your ring here versus what's coming off my ring in my product, okay? You see the difference? So the CH3, there's still a CH3, right? But now I have this ethyl group coming off, okay? Versus before, I had propyl coming off. Do you guys see that? So the ring must have expanded the ring and made the substituent smaller, okay? So let's number the carbons, and I think that will help. I used to, when I was studying for this class, I used to take like pens on my paper, like on the table, and I used to draw the cyclopentane on the table, and I used to rotate the bond to show how it's forming the ring. You know, so if it helps you to do that, by all means, like try that out and see. So you're going to move it like a door hinge, like this, okay? So if I were to take the number 5 carbon, let's say I take the number 5 carbon, this 1 to 5 bond, and like a door hinge, I go whoop, like that, okay? I'm expanding my ring, I go and I move it to attack that positive charge. So once it does that, now I have gained a ring that is of 6 carbons, okay? And sometimes it can be hard to see it. So what I'm gonna do, I'm gonna look at my product. I know that I'm forming a ring of 6, so I'm just gonna draw how it looks in my product. I'm gonna draw a cyclohexane, like that. And then I'm gonna number my ring, okay? And I'm gonna compare my numbers, see which bonds were broken, and see which bonds were formed, okay? So at let's take our number 1 carbon is the one that has a CH3, right? In our product, there's a CH3 at that carbon right here. So right here, I'm gonna put a 1, okay? So at my number, and I'm gonna do all the numbering for the other carbons too. But at my number 1 carbon, I have a CH3 attached, so nothing happened to the CH3. You guys see that? Nothing happened, it stayed there. Then my number 1 is still gonna be connected to my number 2. If you go that way. Now, if we keep going down our ring, it's still going to be connected to number 3. Number 3 will still be connected to 2. Our number 3 will still be connected to the methyl. Our number 3 will still be connected to number 4. Number 4 will still be connected to number 5. And now this is where it gets a little, something changed, right? So we have our number 5. It broke away from number 1. It left number 1. And went and attacked, let's number more. So let's put our 6 here, 7 here, and 8 here. It went and attached itself to number 6. Do you see that where it has the positive charge? So I'll put the number 6 right there. That's So that means if carbon 1 lost a bond, it gains a positive charge. It lost electrons. Does that make sense? If you have any questions so far, like just please ask. It's okay. We went over 9. Okay, so that's what we got. So let's continue. So at our number 6 carbon, we see how 6 is still connected to 7, right? That's our 7. 7 is still connected to 8. So that is our 8. Now, let's go and look at our product. In our product, what do we have? We have a CH3 on the number 3, right? And our number 1, we have a CH3 and an OH that will now get attacked at that positive site. And then at our number 6, we have an ethyl group. Count it, 7, 8, 2 carbons, so it looks good, right? Now all we have to do is like how we did in the other one. You take your weak nucleophile that can go and attack a full positive charge like this, and attach yourself. The OH going up just because in the product it's going up. Alright guys, so we had our water go and attack our full positive charge. So when it did that, we still have a lone pair on that oxygen, right? So now our formal charge of oxygen will be +1. So we'll take some weak base in solution, Br minus, let's use it again. And all we're going to do is deprotonate the hydrogen, the acidic proton, and we're going to put those electrons onto the oxygen, and that is going to give us product B. Okay? So I know, let me make sure I didn't forget any methyls because I do that a lot. Thank God for you. Otherwise, we'd end up with like one methyl at the end. So do you guys have any questions about the entire thing now that we did our first mech together? Yeah. What? Why are we using Br? Yeah, so we have that acidic proton, right? Because it's attached to an oxygen, which is very electronegative, that has a positive charge. Oxygen does not want to have a positive charge. So any proton that's attached to it is very likely to be abstracted. It's more acidic than normal. So you can use the, I'll answer your question too. So you can use the Br minus because it's a weak base that we had formed when the leaving group left. When the leaving group left, you formed Br minus, right? So you can use that, or you can use the H2O that is in your solution. You just have to use some weak base. Yeah. What was your question? Sorry, I answered it. We're on the same wavelength. Alright, any other questions about that? Or we can go to my favorite part. So we're gonna do the synthesis, and for this exam, you guys, they're gonna be testing you about those 4, your big 4, okay? So you need to be on the lookout for that. You need to be on the lookout for E1, E2. Let me put, I like to put SN1 and SN2 first. I'll put SN1, SN2, E1, E2. You're gonna be using these guys, so you're gonna be forming double bonds. So you see some double bonds. And you're also going to have nucleophilic attack. So you're going to be attaching like water to something, or you're going to be attaching an alcohol to something, or maybe, yeah, those are your prime examples. Like when you guys do more, you're going to see it over and over again, okay? And it'll get in your head, I think. So, and then what else you're going to see? Br2 and light. So you can put light as Hv, the Planck's constant time frequency. So you can put that, or you can put light. But you have to include light, that's important. Or you're going to see NBS and light as well. Okay. So these are the reactions that you guys have been taught thus far, so your synthesis, okay? This is your tool kit, okay, for the time being. So when you're doing retrosynthesis, I would suggest before you do anything, just look at what you can start with, right? So it tells you that you can start with cyclohexane. So I'm gonna write at the top in my little starting kit or whatever, I'm gonna put cyclohexane, and then you can also start with alkanes that are 1, 2, 3, 4 carbons or less. So I'm gonna put 4 carbons there or less. So whatever, when I get to my bottom, my starting reagent should be one of those two. So we don't have to form the cyclohexane, thank God. We just have to use it from the beginning, okay? So we're gonna ask ourselves at every step. You need to ask yourself, what should I have had before in order to get what I have? Okay, so we're asking ourselves, what should I have had before in order to get that? And what bonds should have been formed and what bonds should have been broken in order for me to get that? So you put your arrow and you're gonna splice this guy at one side. So we have SN1, SN2, E1, E2, right? We have some double bonds in there, but we also have a connection that has been done by the oxygen. So that is a hint to you that you have some nucleophile that involves that oxygen going and attacking an alkyl halide to give you this as a result. Okay, so you can pick either side you want to be your alkyl halide, and the other side can be your nucleophile. You pick which side you want to have the OH and which one you don't want. So it doesn't make much of a difference. You're going to be using the same reagents, okay? Your pieces will be different. So let's cut it right there, okay? So we're going to take the left side. I'm writing it exactly the same as it is. Okay? We know that a bond was formed between oxygen and this carbon here. So if that's the case, what do I have to have present on that carbon? What did you? No. Did you say bromine? Say chlorine? No? Okay, never mind. So you have to have a leading group, okay? Let's pick bromine because we know that you can selectively add bromine using Br2 in light and NBF in light. So that's why I'm going to put bromine there, okay? And then I'm going to put a plus, right, to say that we have some other piece that came and attacked this, okay? So I'm going to start writing my other side. What I have. Looks like this, then we have double bond and we have double bond, right? At this carbon, we have an O attached, okay? So we need to figure out, are we gonna make this an O minus? Are we gonna make this an OE? And have it go and attack at that site right there. That is an electrophilic carbon. It is susceptible to being attacked by a nucleophile, okay? So, let's look at our alkyl halide. Our alkyl halide, it's primary. It is primary, right here. So that would lead you to go SN2, right? You would rule out everything else, and you would say that this is SN2, not SN1. Right? We know it's going to be substitution because we've added the oxygen on its top. But let's pay closer attention to this group. If we were to have, for example, a carbocation. So in SN2, a carbocation is not formed. But you do have a partially positive carbon there in the transition state. So I'm going to use the carbocation just to show you guys the example. So you can have resonance here, right? You guys agree with me? You can have resonance there? So this primary positive is getting stabilized by resonance. Okay? So that's the option. So you cannot have SN1 normally on a primary, right? But you can have SN1 on a primary that has resonance. Okay? SN1 on primary carbon with resonance. Because in Dr. Bean's notes, she will indicate that if you have a positive charge on a primary, okay, with resonance, in terms of energy and stability, it is equivalent to having a secondary carbocation. So for that reason, we have the OK, we can go with SN1. Does that make sense? We can go with SN1 because SN1 can occur on a primary carbocation with resonance. Okay? For that was just a little demonstration of why we're going to put just OH, not OH minus, because OH like that would give you a weak nucleophile, and basically after this bromine left, it would come with its lone pairs and attack that electrophilic site. And when it does that, it gets deprotonated and everything, but basically, long story short, you get your product. You guys see that? We're forming this bond right there, okay? So we have our weak nucleophile, and then we have our alkyl halide, and we checked it. Now, if you have SN1 or E1, make sure you include heat. You're gonna have heat for both of those guys. So I'll put the heat symbol, I'll put it on the arrow. If you want to write heat, you can write heat as well. So now we need to pick which piece we want to synthesize, okay? So we can start with the left one or the right one, it doesn't matter. But let's just start with the left one, because there's only one double bond, so it may be easier to do that one. So we have this leaving group, we put a bromine on here, and we put a bromine and we put it specifically at the carbon in the allylic position. So that means that it is adjacent to the double bond. It is one carbon over from the double bond. Right? So if we had this before, right, we were able to add the bromine at the allylic position. That's called the allylic position. And you have to use a specific reagent in order to do that. And that's going to be your MBS. MBS and light. So you'll put MBS and light on this arrow, and then you would get our bromine at that allylic position. So that looks good, okay? Make sure you include the light. Okay, these are free radical reactions, so they need light in order to get initiated. So now we ask ourselves, how do we form double bonds? Which types of reactions in this list will form double bonds? E1 and E2, exactly. So when you're doing synthesis, I want you to ignore E1, so I really shouldn't put it there. Just ignore it. We're going to use, whenever we form double bonds, use E2, because the conditions for E1 are the same conditions for SN1. So the problem is that if you use those conditions, you will get major product SN1. So you will get a substitution, and we're trying to form a double bond. So if we do E2, it will ensure that we will get major product double bond. So that's why I am not going to use E1. I'm not going to use something that could act as a nucleophile or base, a weak nucleophile or base. I'm going to use a strong base, okay? And we have different examples of strong bases, and sometimes it'll make a difference which one you use. In this question, we have a symmetrical molecule, right? So the double bond could be connected to any of these, and it would look the same, right? Do you guys agree with me? Let me go back before I start getting ahead of myself and writing stuff. But would you guys agree with me that this is the same thing as that, and this is the same thing? All of these are the same because it's symmetrical. So that's my point. Is that means that no matter where the double bond goes, it's the same product. So we don't have to worry about putting a bulky base, or we can put any strong base that our heart desires. So we can put NaOH, or we can put this tert butoxide, it's called, okay? So this one is going to be bulky. This one is going to be small, okay? Put either one you want. You can put NaOH to involve the spectator ion if you want. So now, if we form a double bond, before, you have to ask yourself, what should I have had before? I should have had a leaving group on my molecule, okay? A leaving group on my molecule, and then an adjacent hydrogen on an adjacent carbon should be abstracted by our base to form the double bond, okay? And there's a specific reason why I placed the bromine in the middle as opposed to here, for example, right? And I'll explain that, of course. But even if you put it here, let's say I put it here, right? Put it here, get rid of this thing that I have, and then we're going to use, that means we have to use this hydrogen to do the abstraction. So remember, we have tert butoxide comes, this is E2, so one time, all at one time. That's how we form that double bond that's up there, okay? This is symmetrical molecule, right? So use Br2 and light. Right? So if we had this guy before, and we use Br2 and light, where is the bromine gonna go? Is it gonna go here or here, like we have in our product? Or let me make sure it's the exact same carbon, so maybe that would make it more clear. Like, is it gonna go there or in the one in the middle? So think about free radical reactions. You're forming a free radical, right, in the middle, right? You're forming it at some point when you have propagation. So what is more stable? Having a tertiary radical or having this radical, where you have primary. This carbon with the radical is attached to only one carbon right there. I shouldn't put another dot, but you guys see how that's primary? Right? And then the other one in the middle has 1, 2, 3, so it's tertiary. Which one is more stable? A tertiary free radical. So for that reason, your product, when you hit this alkane with Br2 and light, it's not going to give what I put as our major. It is instead going to give us the bromine in the middle, because that was more stable to have the free radical in the middle, okay? So now we're able to make a change. So it was really like that. Okay, so the BR has to be in the middle. Our major product will have it in the middle because of the stability, okay? Now, we got down to 4 carbons or less. So are we done? No. I heard somebody, damn it. I wish we were. So basically, firstly, for this right here, you need to make sure for your alkane that we have in the box, you want to write 2 very, what's up? Oh, okay. Oh, it's all about this? Okay. Yeah, I got all excited. No, it's okay. Yeah, so basically, this right here, you need to include 2 very important letters. And these letters will give you 2 points on your test. So just write it, okay? Excess. Not extra small, but it stands for excess, like that, okay? But you can write the letters X and S. So what that means is that you have an excess amount of this alkane here. You have higher concentration of it. And having higher concentration of the alkane will allow you to only monobrominate this into your product. You do not want to form this. You do not want to form this, where you have bromine here, and bromine here, and bromine here, and bromine here, right? We don't want that, right? We want it to just be one time. So if we have it one time and we put our reactant in higher amounts, right, that allows it to just be brominated once. Because you have more of that in relation to the amount of this that you have. And you have more of that in relation to the amount of this that you have. So you wouldn't form a free radical again when the BR gets on there. You would have more of it. So that's why you put the excess. It's so important. Don't put excess for NBS though, okay? NBS is very selective. It will do the job without excess, okay? So now we have to make sure we synthesize our other side, okay? So we have an OH that has been attached, and we have these 2 double bonds. In my opinion, we should address the OH first and deal with our double bonds when we get lower on down, just like we did the others, okay? So what we got, we have this OH getting attached. So the OH has to come from somewhere. It's gonna come from water. Okay, it's gonna come from water, and that means that you must have had an alkyl halide before, such like this, right? And you need to have your leading group, so we'll use bromine, that's quantity. We're gonna put bromine coming up from the carbon that now the OH has been substituted, okay? So what type of reaction is this? This is going to be SN1. This is SN1. You have a weak nucleophile that is water, and it's going and substituting itself for bromine, okay? And then there was a deprotonation, but this is we use NBS in light, that means we would put the bromine on the allylic position to these double bonds. Notice how it would go here or here, and you have a symmetrical molecule, so it does not make a difference which one you're attaching it to, right? It's the same idea. We're running down space. So now we form these two double bonds, and we form double bonds in our other side, so we're going to take the same approach with it, okay? We have to do an E2 reaction, so we want to have a base of some sort. Let's put tertiary oxide, okay? And you can write it with a potassium ion if you want to. It stabilizes it, okay? Let's check it and see. It depends on what we had before. Depends. So I'm putting our cyclohexane part, right? And that means I can't form both of them at the same time. So I'm going to form one at a time. And so for this instance, I'm going to make sure to put my leaving group here, hydrogen that gets abstracted adjacent to it. So whenever I use a strong base, such as tert butoxide, it's going to abstract the hydrogen, push the electrons on. Remember, bromine is going to be pushed off. So this is E2. It happens all at the same time. Bimolecular. Okay, so if that's the case, let me erase our hydrogen since we made sure that's correct, but we erase the arrow. Alrighty, so his question was, can we use any base for this? And so we're using tert butoxide. Now, if we were to have used OH minus, let's see, small base, not bulky, you only have one hydrogen option that can be abstracted. You don't have a hydrogen on this side, right? So for that reason, it's okay to use any base you want because it's only going to abstract that hydrogen. Your product, you don't have options for your product. You only have the double bond can only form right there in that position. That's the reason why I put the bromine right next to it. Like you can only form a double bond right there. You see that? For that reason, you can use any base that you want, okay? You don't have any options for your product. Okay, so let's go backwards and we'll erase the hydrogen because you don't have to show that. Okay, so now you ask yourself, how can I get a bromine? What's up? From the very beginning? Yeah. Why we cut it in half? So yeah, so technically we're going backwards, right? So this is our product, we're going backwards. So technically we're forming that bond. But I put the arrow there just to show where it's getting formed. So you're taking like this part, I'll circle it, you're taking this part and actually forming a bond right there. Yeah, so it's like two separate things that are coming together. And you'll see that trend all the time. That's gonna be your first step, like I would bet a lot of money. Not a lot of money. Not money, I'd bet other stuff, but not money. Exactly. You need to cut it right where the nucleophile, that oxygen was, and where it attached to that particle. Exactly. Good question, Tom. So now, how do we get bromine on the allylic position? We did this before. In this question, I think we did it 3 times, right? So you guys know it now. You guys are pros. So, we have this. Agree with me? We add it to the allylic position. That's what I'm circling kind of. Alright? How are we going to fit this? So now, it got added right here. You see it? Before it wasn't there. We used NBS and light and we got it there. It came. So now, before that we had a double bond. So how do we form double bonds? Which reaction on our list? E2. So it's no E1, so our only option is going to be E2, you guys. So we need to write an E2 reaction, so we can use any base we want. Let's use NaOH. Let's use NaOH for this one, just so we show the usage of another one. This is small base. So that means before we have this, and that means where the double bond is located, we must have had a leaving group and some hydrogen adjacent to it. So we can put bromine anywhere on this ring. Because no matter what, it's going to form a double bond and then using the NaOH, you would form that double bond. So that looks good. Now how do you get a bromine on a cyclohexane? Nice. Br2 and line. So you guys are getting the hang of it. Do like 4 of them? I think you'll be good. You'll start to notice these strands. Now, what else are we going to write so we get 2 points? Good job. So we're going to write excess there because it's... What's your question? Yeah. That's a really good question. So for this specific question, I wish it did matter, so I could have explained an example where it does matter. But where it matters is because, remember, I wish we have extra paper. So it makes a difference because if you have a bulky base, it will give you a different product. And versus if you had a small base, it will give you a different product. Oh, sorry. No problem. So, if you have a bulky base versus small base, it will give you a different product. So the bulky base will give you the lesser substituted product versus the small base will give you the more substituted product, which is known as the Zaitsev product. So that means that you have a double bond with more substituents coming off of it. So it would make a difference depending on what you're trying to form. So if you see that you're forming an alkene that is lesser substituted, then you would go with the bulky base to give you that as your major product. Remember when we were in reaction section, it gave us 2? That's the reason. So when you do more examples, you'll see an instance where it does matter. For this one, we were getting the same molecule no matter which one we used. So you just gotta check this out. No problem. By the way, guys, thank you so much for coming and good luck on your exams. Hopefully we'll see you tomorrow, okay? Thank you. Your panel, of course. Yes. Good luck, you guys.